Today we're making our interiors update automatically, and I have made a small change that will make our interiors just that little bit more realistic that you're not going to want to miss. So let's get to it. With our current setup, when I change the amount of floors, the whole setup breaks with the interiors, as you can see, until we actually move it. So we'll be fixing that today. And the other thing is we want to fix this right here. And something I realized is this door does not actually make much sense. And what I mean is if I move this around and I can see this door here, I have this door in the middle of two rooms effectively. Right? If I look from here, they have a room on the left and a room on the right. Now, if you look around in probably everyone's apartments and just observe the doors, whenever you see a door around, there is a wall that is adjacent to it. That door most likely opens against a wall. Now, there are situations like we have here where there is a door kind of in the middle of a wall and there is another opening on the other side. Now, it does happen, but it is very rare. So if I looked around in my scenario, I have a door to my left and it opens against a wall. My bathroom door opens against a wall. My front door opens against a wall. Every door opens against a wall. And so that got me thinking, well, we don't want to just place a door then randomly on a wall. We want to place it and then have the new wall be offset from that door. So that way, when there's a door spawned, a wall will be off of it. And when the door opens, it will open against a wall. And that's exactly what we're going to be doing. So we're going to change this up a little bit. So that way we have this slightly more realistic aspect of it. Then we can go and build it up from that. Now, one other note, currently with my setup, every floor is random. So if I come down here and I go unlit, you could see this floor, they all have different designs. I have not quite gotten the hang of getting that live update and correct updating to work with the multi-floor randomizations. I have some ideas of how to do that, but all of it is a little bit too manual for what I like. So for the time being, what we're going to do is we're going to fix this up, make it fully dynamic, and then we're going to take it and then using the custom node we have done last time, we can use that and just duplicate it up to however many floors we want. So we'll have nice, correct interiors and all the floors automatically populated. If you're interested in seeing how this is set up, but you have not followed along up to now, don't worry. I'll go ahead and open and explain every single step that we're doing. So that way you can go ahead and pause it where you need to and be able to replicate this for yourself. So let me show you how to modify our interior custom node to get us this result. If you open up your PCG graph, you can go to your generate room walls and we can just open it up and get access to our full graph. So at the current moment, the way it works is we go through all the points. We just set them all to be 0. And then depending on how many wall segments we have, we get a random point, we generate a full wall from it. And then we say, okay, if number of floors that we need is correct, then go ahead and exit out. Otherwise, go ahead and just move them up and then regenerate the entire thing. Then save those points, move them up and regenerate the same thing again and again until we get a unique floor in every aspect. Now that saving of the points from the way I'm doing it currently is not working for dynamically updating. So that is my currently bottleneck and the only reason I haven't done a dynamically updating points yet. Let's go ahead and take all of this and let's clean it up, put it into our loops, and that way we get our full updates back. So I'm going to just detach from here, from this calculate for this point, and I'm going to take all of this and I'm going to move this over. So effectively what we have here now is we're going to grab our execute, get our inputs. For each input, we're going to get our tag data. We're storing the tags and pins just in case. Then we're getting our casting to spatial data, getting our points, getting our PCG points, and from here, we're calculating the furthest point by first saving some local variables to the highest number, and then comparing those numbers and seeing if the current point is smaller than the X or the Y, and then we're storing those two values on the X and the Y. So that way we know what those values are going forward. So that way, once we actually have gotten those, because of our offsets, we don't have walls spawning on top of walls. And the reason this is in the negatives is if I come here and I select this, currently this is positive and positive, and we're offsetting the walls that we're generating into negative and negative. So we're generating them into moving them diagonally left and up relative to this screen. So that's why we need to see what is the furthest left and the furthest back, which are negative Y and negative X. But before we get too far ahead, what I'm going to do is change also this output real quick. What I'm going to do is first I'm going to get our PCG point data and we're going to make PCG tag data, and we're going to be using the same tags and pins here. And it's similar to what we've done in the past, I'll grab our tags and pins, copy that, and plug this in so that way any tags and pins that we had before are still being stored. And from here, we can go ahead and make an array with it. And effectively, we have now recreated this out tag data array. So now I can just take this and plug this in, removing this. So now we're just using our PCG point data as our output effectively. So looking at our old setup, first we were getting a random selected point, and then we were doing a while loop that checks if it is the furthest point, try again, otherwise let's continue on. So I'm going to take this, grab all of this, grab this, I'm going to copy it, and we're going to place it right in here. So what we're going to do is plug this in. On the PCG points, we're going to get ourselves a random array item, and then plug that into a random selected point, and we're also plugging it into here. Now, our furthest point check is just checking our random selected point that we've just set here, and we're seeing if its X is along this furthest point along X, or if it's Y is furthest along Y, then return true. And if it is true, then it's going to try to select another point until it does not select something that is along either of those two walls. Once it has completed, then we know that it is correct and we're good. But once it has selected a point, what we need to do is take our point and see what it is actually rotated of. So we can go ahead and copy this up here. And basically we're going to check how we need to rotate that point, or if we do, because relative to the point, because if I come here, right, we have points in one direction and in another direction. So depending on which side we're going, we need to know what point we need. Is it a 90-degree rotated wall or is it a straight wall? All we need to do is take our randomly selected point, and then we need to break it to get all the information from the transform. Go ahead and split it and plug in the rotation in here. And basically we're checking if the rotation of the point is equal to 90 on the z-axis. So it's rotating 9 degrees within about a 1 degree change, just in case. Sometimes Unreal likes to slightly fluctuate the points. Then go ahead and set it to be a rotated wall. Just make a note of it that it is rotated, and then we're good. Next, what we need to do is get our loop going. So this is going to repeat depending on how many segments we have. So what I'm going to do is grab ourselves a while loop, because while this condition is true, we want to go ahead and keep generating more walls. What I'm going to do is grab ourselves a new variable, and this is just going to be called loops completed. It is going to be of type integer. And we're going to say as long as the loops completed are less than the number of wall segments that we want to make, and our wall segments is how many walls we're generating. As long as that is true, keep doing this. Otherwise, exit out. Because once it has equaled, once we have completed the amount of walls that we have specified in our wall segments, it goes ahead and completes out of here. Now, preemptively, I'm also going to create a stored door point. And these are going to be type PCG points, and it is going to be an array. You can just right click on it to set it to be an array. And right at the beginning of this while loop, whatever points we've had stored here, we're going to clear them. So that way, on every single loop, we're starting with a nice clean slate. And what we're doing with these points is we're taking the entire wall that we're generating, and then we're saying, okay, these are the points of that wall. Let's now take that random point and make one of them a door. So instead of having an array of every single point in the entire environment, once we've gone and generated the first wall, we can go ahead and just say, okay, these are the points of that wall. And we're going to be storing them in the stored door points. From here, we'll go ahead and grab ourselves a point loop, and we're going to get in context, plug that into in context. And our data will be our PCG point data. And then if you go under functions, you can click override, and you want to override the point loop body. When you do, you will open up the point loop body section. And this is also in our functions. You can see under flow control point loop body. So this is the function that we have created from this. Now, unlike a normal function, you cannot add more or less inputs here. It is just hard-coded right now. Hopefully we'll get us more controls over these, as well as the ability to gain more loops in the future. But for now, this is our limitation. So looking back at our original graph, we were doing a condition check to see if we want to place a wall there. So if I open up our condition check, we were taking our point from the array, comparing it to a random point, and depending on certain criteria, we would say, okay, is it going to go ahead and spawn it, or is it not? So what we're going to do is I'm going to take all of this and I'm going to copy it, and we're going to go into our point loop body and we're going to paste it in so that we have a copy of this. Now, if you're wondering why I don't take this condition check and just bring it in, if I come in here and drag it in, for some reason, functions error out inside of these loop bodies, so we cannot use functions directly inside of them, but we can use everything that comprises that function right in here without any issues. We need to get our random selected point, and then we can go ahead and break it, and we're just going to split the transforms on this, and then split the location. So then we have all the same values, and I'm going to hold control and just reconnect X, Y, and Z, and the rotation on this. And we can reconnect X and Y here, and just to make it cleaner, I'm going to duplicate it and reconnect it here on X and Y. So what we're doing is we're checking relative to that rotated wall. If it's rotated, we're using X. If it's not rotated, we're using Y. So over here, we're first checking if the X on one is equal to the X of the other, or if the Y of one is equal to the Y of the other. Basically, we're trying to make it if it is a line. If it is in line, we go ahead and store that information relative to the rotated wall, and we say and on this check. And to make it slightly more organized, I'm just going to move these points around. And assuming that is true, we also are then checking if the Z is equal. Now, we don't actually need to check if the Z is equal anymore because we're not doing multiple floors. And the way we're doing it before, we're also not checking multiple floors. So in fact, I'm going to go ahead and delete it, and then I'm going to remove the pin because it makes no difference as to whether or not the Z is equal, because it is always going to be equal. But we definitely want to make sure that the rotation is the same, because if it is rotated 9 degrees off, then we want to make sure, and we're checking if it is at least within 1 degree, and that is good enough for us. Then where we're checking before, if the loops that it was doing, if it is the first wall, then we wanted it to always just exit out to be correct. So originally the first wall goes all the way across, and then the next ones are off of it. But the first wall, we don't want it to stop anywhere. And for that, we're going to just change this wall spawn index greater than 1. And we're just going to grab our loops completed that we have made, and we're going to check if it is greater than 0. Because if it is greater than 0, then it means it is going to be the second wall, third wall, etc. And that means it is going to go ahead and continue with the checks depending on which side it wants to pick. And if it is not, then it is going to go ahead and just say, yep, that's good. We're good. Let's continue on. Now, after some testing, I found there a different solution to this. So what we're going to do is I'm going to remove this rotated wall. I'm going to detach this. I'm going to remove one of them, and we're going to put wall side here for the index of both, and rotated wall will be here. And we're going to be changing these guys as well. So I'll go ahead and detach this. Effectively, what we're doing is a wall side variable that we're setting a little down the line. Effectively, we're checking which wall side we're going to be using. And for that, we have a function that we have made in the past that is right here. And we'll be tweaking this one just a little bit. So we'll go further in depth in a bit on the changes on this. But basically, we're checking which side do you want to spawn the wall off of, whether it goes up or down relative to how many points there are on either side. But of course, which point it's going to be choosing is relative to the point whether it's rotated or not. So let's grab X first, and we're first going to grab a less than node, plug this into the bottom section, and we're also going to get a greater or equal node, and that is also going to go into the bottom section. And of course, we're comparing the X of one with the X of the other. So we're plugging the X of our points that we're grabbing into the top, and we're going to do that for both of them. So depending on which side it has chosen, it will be either false or true, and it will either be less than or greater or equal. And the reason it's greater or equal is because currently our points are spawning into the positive. So if we have a point in the middle and we have 3 points to the left and 3 points to the right, the one that is itself is going to spawn a wall right. So effectively there's 4 to the right. So it's greater or equal versus less than. And it's going to be similar for the down here, going to be similar for this section. The only difference is it's going to be Y and Y for the points. So we can just duplicate it down and then plug in the same way, false and true. And so now this takes care of the directionality of this. Let's go ahead and detach this return node, scooch to the side, and let's get ourselves a branch node, because that is the full check is checking all of this. And depending on whether it's true or false, we want to do different things. I'll go ahead and grab our endpoint. I'll drag it out, and we're going to go ahead and set members in PCG point. And we're going to grab a second one of these, and I'm going to add a reroute node and plug it into both of these, because from true and false, we're going to be using the same type of node, but we're going to be setting it to different things. On the actual top one, when this condition is true, we're going to set the density to be 1.0. That means a wall has spawned. But if it is false, we need to modify the density. So what we need to do is actually grab our density, and we want to plug this in, but we don't want to plug it in directly. So from here, I'm going to search up a select float, and we're going to plug our density into B. Our A will be 0, and this is going to go into our density. And what we need to check is if this is the first floor, then we want to just set every point that is not the wall to be 0. So effectively, we're going to be left with just 1.0 for all the walls and 0.0 for density for everything else. Otherwise, if there was already a wall there, we don't want to remove it, which is why we're keeping the density on every wall after the first. Search for get loop completed, and we're going to just double check that this is equals to 0. Again, if this is the first index, then go ahead and set it to 0, and then we're good. So from here, we can go ahead and grab our out points. We go ahead and plug these in. Make sure to return value is set to true, otherwise your points will be gone. And here we also need to plug this in, but first we need to store all of these points. So I'm going to go ahead and get ourselves a new variable. I'm going to just duplicate our stored door points, and I'm going to do a stored wall points. So this is going to store our wall points. So every time it goes through the loop and it finds a point, I want to go in here and I want to add the point to the stored wall points. And I want to go ahead, of course, afterwards, output these points from our graph. So we'll be left with just 1.0 and 0 on the first wall, and then we continue on. So now we can exit out of here, and our point loop is complete. Now, if you're finding this tutorial helpful, I would really appreciate it if you hit the like button. It helps me a lot. And while you're down there, consider subscribing to see more awesome tutorials like this. Let's get back to it. So once we have the actual wall all generated, that's great. What we need to do is actually now pick a new point relative to that wall. So I'm going to add a new function, and I'm going to call it select random wall point. And from here, we're going to do something similar to what we've done in the past. So I'm going to grab our point, I'm going to set it. I'm going to check the while loop. I'm going to do all of this. I'm going to grab it, copy all of this, go into our select wall point, paste it in, and I can plug this in right at the start. The difference is instead of our total points, we don't want our total points. We want our wall points. We want to pick a random wall point and store that. And same thing here. We don't want our PCG points. We want the wall points. And from here, grab the while loop one more time. So this is going to go here. Our furthest point check plugs in. But first, we actually want to do one other check. We want to check that it is not the furthest along, but I also would like to see that the randomly selected point, that the density is not equal to 1 as well. Because if it is equal to 1, that means there's already a wall there. And let's go ahead and have it pick a different location if there's already happens to be a wall there. So go ahead and take that, plug that into our condition. And assuming it has not found a point on the first attempt, pick a different point, and then let's get our stored wall points, and let's go ahead and just remove this point so that way it doesn't accidentally grab it again. And then if it somehow runs out of points, we want to just stop this loop. So if it does not find anything that is possible, we want to break this loop. And we do that in the past the same way. We go down the list, and if it cannot find a point, then it breaks it. It breaks our loop. So from here, what we can do is just right click on this point, and we can go ahead and promote to a variable, and I'm going to call it break while loop. And then on completed, you can leave it blank, but I'll just go ahead and for myself, so I know what's going on, I'll add a return node. So this is where it exits out. So at the very start over here, what we need to do is check this break while loop. So we're going to take it, and while it is a not Boolean, so keep doing this until it is broken, and we're going to grab ourselves an and Boolean, plug this in, and this is our condition. So that way we can go ahead and break out as soon as it fails, and we can take our select random wall point, plug this in here, and get this right in between. Now let's make a new loop, and we're going to make a variable loop. So if I drag out and search variable loop, this loop allows us to have multiple outputs, but really we're just using it effectively as another point loop because we're keeping the amount of points we're generating, but because we cannot have multiple point loops in PCG currently, I'm just using a variable loop as a point loop effectively. So I'm going to grab our in context, plug that into in context, and our out data is going to plug into the in data from here. So I can drag it out, and then just like the point data, we can override variable loop body. So for a variable loop, all this is going to do is take our wall, and then it's going to make one of the points to be the door, and we also need to store that point of the door so we can use it to spawn the wall off of as well. So we're going to take our point and we're going to break it so we can get access to our transform. And we're going to actually compare if the transforms of this are actually equal to a random selected point. By taking a random selected point and breaking it, we can compare the two values. So effectively, we're just going through this entire list and we're checking, hey, is this point that point? If it is, great, then we're good. But if it's not, then continue on. We only care about that one point. So we'll go ahead and plug that into our branch. And then if it is that correct point, we can go ahead and set the members on it by grabbing a set members in PCG point. And we're going to be setting the density of it. And we're going to be setting the density to 0.6. Now, the 0.6 is not required to be specifically 0.6. We're just using 0.6 because in our PCG graph, that is the number we have filtered to spawn the points for the door. So if I select this point here, that is spawning our doors inside. We're just selecting 0.6 because that is what we have set it to. You can, of course, use a different value here if you would like. Now, once it has picked a single point, we go ahead and save it to our stored door points. We go ahead and add it here. So we store that information. Now, just so you know, you cannot store global variables in here. So if I, for example, wanted to set floors to be something here, and just like this, and I compiled it, it says variable floors is read only within the context and cannot be set to a new variable, new value. So we cannot set global variables. We can only set local variables inside of these loops, but we are able to add and remove things from arrays that are global variables. So that way, this is my workaround for that aspect. So once we have this, we need to go ahead and return it. So for the return, I'll go ahead and right click on the return value, promote it to a local variable. And this is going to be just our stored points that that we're going to be exporting. And we go ahead and grab those and we add the point here as well. So we add this point to our output and then we plug that in. And then assuming that it is not that point, assuming it's one of the other points, well, that makes it a lot easier. We go ahead and just grab these stored points, duplicate it down here. False plugs into this add node, and we can go ahead and just get ourselves a reroute here and plug this point in here. So if it is the actual door piece, set it to be 0.6. Otherwise, just go ahead and exit out of here. We're good. We don't need to do anything with it. And that is pretty much it for the variable loop. Once it is complete, once we're back into our execution graph, we can go ahead and store our PCG point data to be this. So that way, the next time it goes through this loop and grabs our PCG point data, it is using the output of the total loops that we have completed. So it is basically reusing the point data on the loop every single time. So we don't need to store it somewhere and then load it up at a later point. Now, as always, I do offer all the files for these projects, for these tutorials on my Patreon, where you can join these wonderful people that help support what I do. It means a lot to me. I really appreciate it. Or if you just have some questions or would like some support on the tutorials or anything like that, feel free to drop by the Discord. The links are always in the description down below. Again, thank you so much to the patrons. Let's get back to the tutorial. Once it has gone through this loop, it has done everything we need. So at this point, we can take our stored wall points and we can clear those out because we no longer need them. We have made use of them. So let's go ahead and clear it. So that way the second time around, this is starting up to be a clean loop. And then we can go ahead and iterate our loops completed by just grabbing ourselves an increment int, plugging in it. So this way, this goes ahead and increments. And then we need to check whether the loops completed is not equal to the wall segments that we have specified. Because the next stuff we're going to need to do is only important if this is not the last loop effectively. There's a few ways to do the checks. This is one of them. So if this is not the last loop, then we also want to go ahead and get some more information from here. Starting with getting our stored door points and getting our point that we have stored. And then we want to go ahead and set members in this point off of true. And we want to modify that transform. We have stored this door, but now we want to spawn the wall off of it. But the wall is going to be rotated 90 degrees. So we have a rotated point transforms function that we have made in the past. I'll go ahead and duplicate it over and plug this in. If I open it up, all this is getting a random selected point, and then it is just making a new make transforms. And the only difference is the rotation Z is based on the rotated wall. So if the rotated wall is true, then it is using 0. Otherwise, it is using 90 degrees, and that is the plugged in. So this goes ahead and rotates the wall relative to this point. After which we go ahead and just set the new point from this struct that we've just set. So we just taken the point and then stored it as a 90-degree rotation. Now, because we have stored it as a 90-degree rotation, our rotated wall here is no longer accurate. So we need to actually go ahead and reset it over here. So the easiest way to do that is to grab our rotated wall and just say not Boolean. And basically all this is going to do is invert the rotated wall and store it back onto itself. Fantastic. And of course, as we have used before on the point loop, we need to now grab ourselves this here, this calculate distance to edge. So I'll go ahead and grab this, and you can go off of the PCG points originally. I'll go ahead and copy all of this, paste it in. If I open up this calculate distance to edge, let's make some modifications to this so that way it's a little bit nicer. First of all, I'm not going to comparing the rotation because the rotation doesn't matter, and I'm going to plug this in just directly. So we're going to remove that. The reason the rotation doesn't matter is because if you have a point in the middle here and there's 2 points overlapping on the right and 2 points overlapping on the left, the number is still going to be the same. If there's 4 versus 2, it's still 1 is going to be greater. So because of that, as long as we're doing the same math on both sides, it doesn't matter if the points on the right are doubled and the points on the left are doubled, or they're all singles and singles. So because of that, we can go ahead and just remove that and not have that check entirely. One thing we do need to change though is this rotated point transforms. What we need to do is grab our random selected point, break all the information and split the transform, and then split the location of that. And then we can hold control and reconnect the X to the X and the Y to the Y and removing this random point transform. So what this is doing is relative to whether the wall is rotated, it is going to go ahead and check whether the X or the Y is equal to the X or the Y. So it makes sure that things are in a line. And once it knows the points are in a line, then it goes ahead and continues. So assuming that they're in a line, then it goes ahead and compares the other axes. So it says the X's are correct. Okay, well now relative to the rotated wall again, compare the Y of one versus the Y of the other. Or if the Y is correct, is matching here, compare the X of one versus compare the X of the other. And relative whether one is greater or less than, we store just a variable that says wall side A or wall side B. And these are both local variables, so they get reset on every cycle. And it goes ahead and increments it. And then an output, what we're going to do is just change this to be wall side A is greater or equal to wall side B. And that is going to be our output here. So a small change, a little bit less here. But all this is doing effectively is, again, calculating how many points are to one side versus the other side of our original point. And then storing that information as a true or false as to which side to pick. So if we come here and we change the number of floors to be 1, you'll see we have our walls being generated. So if I go ahead and just regenerate this, you can see we have, this is our original wall. It has picked the door, and then off of the door, we've spawned another wall, and off of that wall, we've spawned another wall. So if I just hit compile on the interior walls, it will automatically regenerate. And again, it has picked this wall as the default, then it's picked this wall, and recompile, and again, same thing, recompile. So now what we can do is go to our PCG building, and over here, we could change the amount of wall segments that we need. We can specify 5, for example, and then unhook this generate room walls, and we're going to get our duplicate points up that we've made last time, and we're going to plug this in directly, plug that into our source. We can unhook the amount of floors from here and plug that into our duplicate floors up, and then on our duplicate points up, we don't want a unique bottom or top floor, but now, once we hook that up, I can come here, and I can select the number of floors to be 2, 3, 4, etc., and you can see it is now duplicating the points up for each one. So if I come here and go unlit, you can see it's the same design every floor, like I mentioned before, but it is now dynamically updating on no matter what amount of floors you've specified, you now get the correct result. And as before, our staircase is cutting through on every single floor and is removing walls if it was going to intersect. The main thing is now everything is fully dynamic. It is updating correctly. It makes more sense to me to have the doors generate the way they do right now. So hopefully that is going to be good enough for you guys for the time being until we figure out a better solution. I hope you guys have a fantastic New Year's, and I'll see you guys in the new year with more awesome tutorials like this. Take care. Bye!